And we are heading to the next presentation on our stage, Bob, which is titled Large-Scale Hybrid Quantum Computing Solution for Linear Systems of Equations. And the speaker is Michael Perelstein. Michael is a quantum algorithms development project manager and team leader at Terra Quantum. And he's also an experimental quantum physicist at Aalto University and quantum algorithms developer at the Moscow Institute of Physics and Technology. Now, I would, of course, be interested in how that works together. I guess you're not working at both locations physically, but I don't know if we have time for this to answer. So I'll just leave the floor to you. I'm looking forward to your interesting presentation, and thank you for being here with us.
Yeah, thank you very much for this kind introduction. So greetings from Helsinki. Actually, I'm here based in Helsinki at Aalto University. So yeah, I'm a quantum physicist and manager of quantum computing projects at Terra Quantum. And first of all, I would like to thank our organizers for this wonderful opportunity to present our recent results in a hybrid quantum algorithms development, and particularly the hybrid solution of linear systems of equation on a large scale. So the tantalizing promise of quantum computers is that they can do some specific tasks much faster than classical machines. And many experiments, for instance, various quantum supremacy experiments, prove that it is indeed the case. And quantum-based computation can potentially simplify the basic calculations necessary almost everywhere. And one of the most fundamental computational problems is the solution of the linear system of equations. And this problem arises in various subroutines in big data processing. For instance, some complex physical simulations can be performed, such as the heat transfer analysis or electromagnetic simulation or aerodynamics and etc. However, classical methods that linearize the partial differential equations and solve the corresponding linear systems, they fall behind when analyzing highly complicated dynamics. Besides all that, we can analyze sophisticated time processes with the help of the quantum algorithms. And one of the advantages here that we actually do not need to measure the whole quantum state, and the whole analysis can be performed on the quantum machine. And this has application in financial services, machine analysis, for instance, in some anomaly detection, and etc. And also some quantum optimization can be performed in that way. And also, of course, linear algebra subroutines arise in machine learning, and the quantum algorithms for linear systems can significantly speed up various machine learning frameworks. So before going into the realization details, let me briefly present to you our general framework of the quantum algorithms. So here's a little bit of math. So we analyzed the quantum algorithm for linear system solution that is based on the quantum phase estimation procedure. So Haru, Hasdimi, and Lloyd firstly presented this in 2009. And the problem is formulated as follows. So the matrix A and the vector B are given, and the vector X should be found. And using then some simulation, we can encode the matrix into the quantum circuit as the quantum operator. And vector B could be encoded in the initial quantum state in the quantum amplitudes. And as a result of the algorithm, the vector, which is proportional to the solution, will be encoded in the same register as vector B. So in general, we can divide the quantum circuit, the full quantum circuit, on a gate-based quantum device into 3 parts. So ancillary qubit is required for a matrix inversion. Then phase qubits, they basically keep the eigenvalues of the matrix, and also register qubits. And the latter consist of the vector B at the beginning of the algorithm and the solution vector at the end of the algorithm. So in order to benchmark this algorithm, we consider a specific problem that in our view is suitable for current noisy intermediate scale quantum devices. So first of all, for this particular analysis, we omit this Hamiltonian simulation and the matrix encoding, and assume that this part is computationally easy for now, because it is indeed the case in many problems. And that gives us the tool of defining the linear system through quantum circuit. And here we introduced 3 types of matrices. So the first one is implemented through a single qubit gates. So the quantum state is just a tensor product of a single qubit gates, and we call this TP1. The second type is more complicated. And basically here, it's a tensor product of 2-qubit gates. And we divide the circuit into clusters of entangled 2-qubit substates, and that's called TP2. And the latest one is the most complicated circuit where all qubits are entangled, so it is not actually a tensor product and TP. And one can consider these three types as basically an approximation of some Hermitian matrix with different level of accuracy. So TP1 is the roughest one, and NTP is the most accurate. And moreover, to simplify the quantum phase estimation procedure, we assume a fixed spectrum of the matrix. And once again, this is indeed the case in various, for instance, differential equations. So this assumption is actually not far from a real-life problem, but it simplifies the quantum realization significantly. So for further simplification of the quantum circuit, we employ some methods for complexity reduction by simplifying the single qubit gates and also using hybrid approach. So the hybrid approach is particularly interesting. That allows us to reduce the number of phase qubits, so this second group of qubits. Since in the binary form, the last bit of all eigenvalues is actually 1 because of this fixed spectrum, we can consider this bit as a classical one and just eliminate it from the circuit. So before this trick, we had 3 phase qubits because there were 3 bits, but now we have only 2 phase qubits. And it sounds not as a significant improvement, but actually it is. So you can see the circuit before this improvement on the top, and there are a lot of control operations, control unitary operations, which are very complicated. And here we have just basically a single control unitary operation. So the reduction of the complexity is significant. And also on the right-hand side, you can see the improvement in circuit depth. And blue points here are for initial circuit for different matrix types, and red ones for the process one. And the problem that they solve is the same, but this hybrid approach and simplification of the circuit allows us basically to reduce the circuit complexity. And in total, to solve that problem with n variables and n equations, we need just log n plus 3 qubits overall. So now we can move to the results of the implementation of this algorithm. So here you can see the very simple linear system that is given by the following matrix and following vector. And basically, we can solve it using pen and paper and show that the solution of this problem should be encoded in this quantum state. So for instance, if we have a fault-tolerant quantum device and we solve this following problem, we will get this quantum state. And for this task, we need just 4 qubits. So here you can see the density matrix of the quantum states obtained experimentally on IBM Open Quantum Superconducting Processor. And as you can see, these quantum states obtained are pretty close to the dashed one, which is the theoretical one. And the average fidelity with this way is about 50–60%. However, assuming that our processor can provide the solution with a high fidelity, we know that the eigenvector corresponding to the largest eigenvalue should be proportional to the solution. So just a little bit of classical post-processing after the solution. And utilizing this post-processing, we obtain the following solution of the Johannesburg quantum processor unit from IBM that coincides with the actual solution with 97.5% fidelity. So this is pretty high for current NISQ devices. However, for the large-scale analysis, for the large-scale solution, we can't get the whole quantum state anymore because it requires full-state tomography whose complexity grows exponentially with the increase of the system size. So in order to characterize the fidelity of the solution, we perform the projection of the quantum state on the z-axis and extract the projection of the solution. And for instance, in different, let's say, electromagnetic simulation, we need to calculate some mean energies of the field. You basically do the same. You got the solution, and then you calculate these mean values. And we employ a similar cross-entropy benchmarking approach as in Google's quantum supremacy work to compare the projections of the quantum states. And we also average this value across random linear systems. So we have a few hundreds of random linear systems here. And the fidelity of our algorithm as a function of the circuit width, so the size of the linear system, is presented on the right-hand side. For the high-performance simulator with an embedded noise model and the actual experiment conducted on IBM quantum devices. And we also plot here so-called digital error model that incorporates all uncorrelated errors in the quantum processor. So just the readout, single qubit and 2-qubit gates errors. And while the simulator with the noise model is in a good agreement with the digital error model, the real experiment data is actually vastly different. So the measured fidelity is almost independent on the matrix type, despite the significant changes in corresponding circuit. And it was actually confirmed earlier that the gate errors are correlated in some of the IBM machines. And this could be really the case in here. Nonetheless, we expect that there are some advanced equipment combined with the necessary precautions against these correlated errors, that's so-called like partial filters, will provide the fidelity behavior according to the digital error model. And what is interesting from this experimental result that we solved the large-scale linear system of the NTP type with a 0.04% fidelity. And this is a record-breaking result for a size of linear system that was solved on a real quantum hardware. So now if we compare the solution of the exact same problems of the solution of the linear system with limited fidelity, and we compare it with the supercomputers from the past, some very impressive and significant devices, we can see the noticeable quantum speed up. And our solution implemented on IBM hardware outperforms such computers as Atlas, Trace, SCSCI Red, and so on. But of course, it is still slower than the modern supercomputers, which is not a surprise. However, in the processing of the 50-qubit problem, because here we employed only 20 qubits, but when we consider 50-qubit problem, it will be impossible for classical devices to keep up. And such a dramatic increase in speed is just an experimental evidence that the hybrid quantum computing, so the proper quantum algorithms, will surpass the classical computing industry that ran in the 20th century. So in general, a purely classical solution of this problem with such advanced method as Casimir subspace method or conjugate gradients and so on cannot tackle this problem faster than in n² time. And despite all the simplification that we made with the fixed spectrum, like block structures and so on. On the other hand, the algorithm implemented on a fault-tolerant machine provides, of course, exponential speed up, and it's far more efficient than GPU or CPU, and the scaling is logarithmic in n, where n is the size of the system, or the dimension of the problem that you're solving. And however, since we live in the NISQ era, and we for now don't have these machines, the quantum-inspired solution, which is basically the circuit emulation on a high-performance device, looks very promising, providing polynomial speed up if you compare with the just pure classical solution. And for instance, if we compare the abstract 100K core supercomputer that realizes the quantum simulations and superconducting quantum processor unit, we find that the quantum approach, of course, outperforms classical computer sets something about 50 qubits or a bit more. However, for that comparison, we employ general Schrödinger simulation, which is just the straightforward simulation that includes matrix multiplication. And we know that more advanced quantum simulation approaches, such as tensor networks, allows for a solution in a polylogarithmic time. And this kind of quantum-inspired solution would show the power of quantum algorithms even more vastly, demonstrating the algorithmic quantum advantage. And in order to implement our solution and leverage the full power of a high-performance computing, we established the hybrid quantum computing platform. It's called Qmware. And the service and software are powered by a high-performance multi-node hardware that can virtualize up to 40 qubits. And these are virtualized qubits in there without noise, so this basically a fault-tolerant machine. And what is amazing, any application built on a Qmware hybrid quantum cloud with virtualized qubit will also run on upcoming native quantum processor. So you can just take out this simulator and place here a quantum processor unit, and it will work as it worked before. So we provide all layers starting from the hardware, both classical and quantum interface, low-level software, high-level software, and also application layers that we now are working on. So we also provide an efficient connection between the quantum processor unit and the classical subprocessors, which is crucial for successful implementation of the hybrid algorithms, and not only linear solvers, but many variational algorithms. And our nodes have a large amount of RAM that is highly important for the hybrid quantum data processing. And using the full potential of our RAM, we can solve 137 billion equations with 137 billion variables. And it is far beyond the capabilities of a purely classical machine and classical algorithms. So the Qmware was established to make this smooth transition from classical computing to a hybrid quantum computing. And that transition is just unavoidable in the future. And the main idea behind hybrid quantum computing is utilizing classical resources to find a problem's hardcore and delegate this hardcore to the quantum processor, or vice versa, taking quantum algorithm whose bottlenecks would be eliminated by classical improvement, as I showed you with this algorithm for linear solvers, because the circuit at the beginning was very complicated, but we simplified this with the classical embeddings. And Qmware anticipates that both these approaches, classical to quantum and quantum to classical, lead to disruptive applications in the most demanding computational problems. And these problems in financial services, such as discrete optimizations or modeling, in engineering, such as solving partial differential equations, and basically reducing them to linear systems of equations. And also logistic, medical, and energy technologies, such as various quantum machine learning models. And that brings me to the end of my talk. So I presented our recent results on the hybrid quantum algorithms for a linear system that was implemented on a noisy intermediate scale hardware from IBM, and also high performance simulator Qmware. And the experimentally implemented quantum solution of this 130,000 dimension problem is a record for linear system solution on a quantum computer, and it demonstrates the algorithmic quantum advantage over classical approaches. And beside this, realization is an excellent benchmarking for a quantum hardware to investigate the correlation in errors and overall performance in these quantum phase estimation-based algorithms. So our future plans and our current work aims at efficient data encoding, so we can process larger classes of matrices. And also now we put a lot of effort into the investigation of the differential equations for physical and biological simulation based on the linear system solver. And right now we're working on the implementation of these quantum-inspired solutions on our Qmware machine. So thank you very much for your attention. If you're interested in details of our work, you can check the archive preprint on the linear system solver and also our Qmware website for more use cases. And now I'm happy to answer your question.
Thank you so much, Michael, for this very interesting and inspiring talk. It's always impressive to me to see those achievements that you've already made there, both on the real quantum computer that you've worked on, as well as for your hybrid approaches. And I have a feeling that this hybrid approach of really trying to combine the possibilities of quantum computers, even early quantum computers today, with classical computing approaches, and getting the best of both worlds is a way to go for the next coming years for a lot of the early quantum computing that we will see. As with the other speakers, Michael will be available for you for the next 15 minutes in the speaker's corner. So if you have further questions or would like to engage in discussion with him, please feel free to approach him directly in the Meet the Speakers room. We here on Stage Bob are going into a short break, a short coffee break of about 10 minutes. And you can use the time to just get a coffee or do other things, just relax your legs maybe after a few hours by now. But we will be back in 10 minutes. We are also using this time to show you a video. If you got your coffee and would like to watch a video of our upcoming events at Bitkom, we are hosting, of course, not only this Quantum Summit, but a lot of other very interesting formats. There's more of those interesting events coming up this year, and you will learn about them in this video in the next 10 minutes. We will see each other again here at about 5 p.m. or exactly 5 p.m. actually, with the next 3 talks then. See you in about 9 minutes by now.